Howdy Pre-Calculus, coming at you with a new video. This was the one that was out of order. Part 2 is coming at you for Monday's assignment. This is going to be a relatively short lesson compared to some of the things we've seen in the past, really because absolute value has one main theme and then it just applies a bunch of math from previous things we've learned. So still know how to work with quadratics, factoring, ... So I got 4 examples for you. Let's get to it. First one, it's example 9 from page 50, so go ahead and follow along in the book if you want to. The basic idea is that these absolute value bars really need to be isolated. It's very much easier to compare a group of absolute value terms with just either a constant on the other side or potentially even like a variable value. So what I need to do is really follow the fact that this is multiplication, this is addition. So I could technically look at this as, hey, if I said that some plug-in variable u is the same as the absolute value of x minus 5, remember when we did those quadratic structures where we said u is equal to some term and then we wrote it as u squared, u, and then a constant? You can kind of think about it this way. Like, if this is just 2u plus 3 equals 9, it should be pretty clear what you're supposed to do in order to solve that. You're supposed to subtract 3 from both sides, and then divide by 2. So u is equal to 3, which means x minus 5 under the absolute value equals 3. So I'm bringing the absolute value back, and hopefully that makes sense. Now, I introduced the whole idea of using graphs of the left-hand side and the right-hand side to make some sense of things when we're not quite sure computationally what we're supposed to do. So here's what I'm going to do. Turn this thing off. I am going to graph the left-hand side here and then graph the right-hand side. So think of y equals 3 is the right-hand side of the equation. It's just a horizontal line at 3. The absolute value of x minus 5, if you'll recall from Math 3, is kind of a pair of lines that come together in a V term. Absolute value basically means, all right, part of it's a negative slope and part of it's a positive slope. It's shifted right 5 units. Okay? With a slope of 1 over 1 when it goes in this direction, and negative 1 over 1 when it goes in this direction. Now, I'm not saying you have to know how to graph these things just yet in this pre-calculus course. What I'm saying is we better be getting 2 answers, because there's 2 spots where 3 intersects with x minus 5 absolute value. So what's the deal with these? Well, what we know is that if you take the absolute value of an inside, it makes anything that came out negative a positive value, because absolute value is kind of the distance it is from the origin. So there's certainly the positive distance, but you also have to keep in mind that what if this distance was inherently negative inside? Yeah. So you're solving those 2 equations. So they intersect at x equals 8. Looks like that's this one. 1, 2, 3, 4, 5, 6, 7, 8. And then it's also going to intersect at 2, which I guess I didn't really graph it accurately. But that's okay. There's grace for that. Now, because I have this graph in front of me, I don't think I need to check these 2 solutions. But that's not to say that we won't check them later, because look at what we did. We took something that was restricted very heavily in absolute value, and we just said, poof, It's gone. It doesn't matter. And that seems to be changing the fundamental quality of the equation. Just like when you had a square root that turned into a non-square root, it changed its fundamental nature, and we had to check those for extraneous solutions. So, spoiler alert, you're going to have to check for extraneous solutions when you do absolute value later on. All right, let's check this other one here. This is on page 53, it's number 27. Kind of the same moves. It looks like it has identical structure to it. So I'm not even going to do the U substitution. I'm just going to say get the bars by themselves. Get the absolute value quantity by themselves before you do any of this business of dropping the bars. So add 5 to both sides. That gives me negative 6 on the right-hand side. Divide by 3. And I get the absolute value of x plus 1 equals negative 2. Now again, to get some perspective, I'm not just going to drop the bars, solve, and then make one of them the opposite of negative 2. I'm going to graph that thing. This plus 1 means it shifted left 1. And then we're trying to figure out where it intersects the line y equals negative 2. Well, as you can see, y equals negative 2 is never going to intersect a curve that goes up and out forever. So there's no solution to this equation, which makes perfect sense. The absolute value of x plus 1 must yield a value that is greater than 0, which cannot equal negative 2. A positive number cannot equal negative 2. So you could right off the bat say, hey, if there's an absolute value quantity put side by side compared to a negative number, you say it's not equal to it, so there's no way that that equation will yield any number that works. Now we're going to try the 2 examples that are on the actual notes document that I'm attaching. The first one is the absolute value of 3x minus 4 plus 5x is equal to 7. So what we'll do first is get the bars by themselves. You know what? I could graph it like I did on those previous 2 examples. Let's just drop the bars and work it out, though. It seems like you could probably, drop them, solve it as is, and then after you drop them, you're going to, over here we said, I just erased it, so yeah, that's useless now. But what I said was that this has the potential to be either positive or the negative version on the outside. So what I'm going to do is make it a negative version. I'm going to distribute a negative through to the 7 and the 5x. Okay? So notice the difference? These were the same. I'm just going to assume that everybody's pretty confident with solving equations of this caliber right now. Pretty tame. So I got 8x is equal to 11. You divide by 8, and you get x equals 11/8 or 1 3/8 or 1.375. I'm just going to leave it at 11/8 for the time being. Okay. Do the same thing over here. So negative 2x is equal to negative 3. If you divide up, you get 3/2. Okay, so let's check it out. The absolute value of 3x minus 4 would be shifted right 4/3 of a unit. You got to do some factoring here. The 3 needs to be taken out of both of these terms. So it kind of starts here, and this 3 is going to make it steeper, skinnier. It's going to stretch it. And you also have a line y equals 7 minus 5x. So it has a starting point of 1, 2, 3, 4, 5, 6, 7. And it's going to go down 5, right 1, down 5, right 1. It's going to do something like this. And I'm not sure if it's going to cross through at... I think it's going to cross through at 2 different spots, but I'm not entirely sure. So here's what I'm going to do. Instead of relying on this graphic version every single time, by the way, this looks terrible. So for those of you looking at this with like great mathematical knowledge behind your back, please don't judge me. Okay? You can just plug this back into the original equation and check your answers to see if they work. Now, when I say original, I just mean the equation version before you got rid of the absolute value bars. So you don't have to go all the way back to this original one. You could try this statement right here. So 3 times 11 eighths minus 4 in the absolute value. Does that equal 7 minus 5 times 11 eighths? And you can use your calculators on this just to save time, right? So 3 times 11 divided by 8 minus 4 is 1/8 inside the absolute value bars, which gives you 1/8. Does that equal 7 minus 5 times 11 divided by 8? It does. So this one checks out for sure. When you try the next one, I'll just use the same space. Again, if you needed to look at that, pause it, rewind the video. 3 times 3 halves minus 4 versus 7 minus 5 times 3 halves. Oh, this is going to be the absolute value of a half, which is a half. And this is going to be 7 minus 15 over 2. I believe that's negative a half. Oh, it is. Okay. So there's a situation where you get an extraneous solution. You change the fundamental being of this equation, and it rejected that solution. Extraneous. All right. I don't know if I can get through this last example in 2 minutes. Let's go for it. All right, last example. You got 2x squared plus 17x in the absolute value bars equals x plus 1. Okay, drop the bars. Solve that first equation. Drop the bars. And solve the negative version of that equation. So negative x minus 1. They're both polynomials. That probably need to be plugged into the quadratic formula. I mean, just eyeballing this right now, there's no 2 factors of negative 2 that give us 16, all right? So plugging it into the quadratic formula, negative 16 plus or minus the square root of 16 squared minus 4 times 2 times negative 1 all over 2 times 2. You do the same thing for the one over there. All right, I'm going to check them. So the first one gives us x is approximately 0.062 and negative 8.062. This one over here gives us approximately negative 8.944 and negative 0.056. All right, your job is to test all of those into the original equation. I'm not sure I have time on this video to do all that, so I'm just going to put the answer in the comment section or the whatever thing, and yeah, I'll see you guys next time.